Comprehensive Guide to Designing and Installing Solar Photovoltaic Systems. 1. Design and installation of solar photovoltaic (PV) systems. Designing and installing a solar PV system involves systematic steps to ensure optimal performance and reliability. Below is a detailed process. Step 1. Assess energy needs. Calculate daily energy consumption in kilowatt-hours, kWh. 1. List all appliances and their wattages. 2. Estimate daily usage hours for each appliance. 3. Multiply wattage by usage hours to find daily energy consumption. Example. 1. 4 LED lights at 10 W each times 5 hours per day equals 200 watt-hours. 2. Refrigerator, 150 W times 24 hours equals 3,600 watt-hours, 3.6 kilowatt-hours. Total energy requirement. Add all consumption values to find the daily energy need. Step 2. Determine system size. Estimate solar panel capacity. 1. Divide daily energy consumption by the average sunlight hours in your location, e.g., 5 hours per day. 2. Add a safety factor, 20-25%, for energy losses. Choose the number of panels. 1. Calculate total panel wattage needed, e.g., 1,250 W. 2. Divide by the wattage of a single panel, e.g., 300 W. 3. Panels required equals 1,250 W. 300 W equals 5. Text, panels required, equals, frac, text, 1,250 W, text, 300 W, equals 5 panels. Step 3. Select system type. Grid tied system. 1. Connected to the local electricity grid. 2. Uses inverters to supply power to the home and sends surplus power to the grid. Off-grid system. 1. Independent of the grid, relies on battery storage. 2. Ideal for remote areas without grid access. Hybrid system. 1. Combines grid-tied and off-grid features. 2. Uses batteries for backup during outages. Step 4. Choose components. Solar panels. 1. Types. Monocrystalline, high efficiency, polycrystalline, lower cost, thin film, portable applications. 2. Size. Based on wattage and available roof space. Inverters. 1. Converts DC power from panels to AC power for appliances. 2. Types. String, micro-inverters, hybrid inverters. Battery bank. For off-grid, hybrid systems. 1. Stores excess energy for use at night or during outages. 2. Types. Lead acid, affordable, lithium-ion, long lifespan. Charge controllers. 1. Regulates power from panels to batteries. 2. Types. PWM, cost-effective, and MPPT, high efficiency. Mounting structures. 1. Securely attach panels to the roof or ground. Wiring and connectors. 1. Properly rated cables and MC4 connectors for efficiency and safety. Step 5. Installation process. Site preparation. 1. Assess roof orientation and tilt angle. Optimal angle is the latitude of the location. 2. Ensure the roof or site is free of shading during peak sunlight hours. Mounting structure installation. 1. Install structures at the correct tilt angle. 2. Use corrosion-resistant materials for durability. Panel installation. 1. Attach panels securely to the mounting structure. 2. Use spacing to allow for airflow and cooling. Electrical connections. 1. Connect panels in series or parallel based on voltage and current requirements. 2. Install an inverter and connect it to the main distribution board. 3. Integrate charge controllers and batteries if applicable. Safety checks. 1. Ensure grounding and lightning protection are in place. 2. Inspect wiring and panel connections for faults. Step 6. System testing. 1. Test energy production to verify that the system meets the design specifications. 2. Check battery charging, if applicable, and inverter functionality. 2. Applications of solar PV systems residential use. 1. Powering homes, lighting, and small appliances. 2. Reducing electricity bills via net metering in grid-tied systems. Commercial use. 1. Powering office buildings, factories, and malls. 2. Lowering energy costs and increasing sustainability. Industrial use. 1. Powering heavy machinery and equipment in remote locations. 2. Integration with diesel generators for hybrid setups. Rural electrification. 1. Providing electricity in remote areas. 2. Water pumping systems for agriculture. Portable and emergency use. 1. Solar chargers, lanterns, and power banks. 2. Backup systems for disaster-struck regions. 3. Limitations of solar PV systems weather dependence. 1. Reduced efficiency during cloudy or rainy conditions. High initial costs. 1. Expensive upfront costs for panels, batteries, and installation. Energy storage challenges. 1. Batteries add significant cost and require maintenance. 2. Limited storage capacity for off-grid systems. Space requirements. 1. Large systems need significant roof or ground space. Maintenance needs. 1. Panels require cleaning to maintain efficiency. 2. Batteries and inverters need periodic servicing. Efficiency. 1. Typical conversion efficiency is around 15–22%. 2. Dependent on sunlight availability and panel quality. 4. Necessary components for solar PV installations. 5. Sizing of components solar panels. Example. 5 kWh per day divided by 5 hours sunlight equals 1 kilowatt. Text. 5 kWh per day. Div. Text. 5 hours sunlight equals 1 kilowatt. Inverter. Example. For 5 kilowatts load, choose a 5 kilowatts or 6 kilowatts inverter. Battery bank. Battery size equals daily energy need. kWh. System voltage, e.g., 48 volts. Text. Battery size equals frac. Text. Daily energy need. kWh. Text. System voltage, e.g., 48 volts. Add 20–30% safety margin. Charge controller. Example. For a 48 volts system with 1 kilowatt panels, use an MPPT controller rated 20A. Conclusion. Designing and installing a solar PV system requires careful planning to meet energy needs efficiently. While solar power offers sustainability and cost savings, it has limitations like weather dependency and high initial costs. Selecting the right components, proper sizing, and regular maintenance can maximize the benefits of solar energy.